Welcome learners. I am Pavan Kumar, Assistant Professor in Mathematics, School of Sciences, IGNOU. So today we shall discuss about the course Graph Theory. Namely, I shall give introduction to graph theory. Graph theory is one of the elective courses offered at IGNOU in the program MSc in Mathematics with applications in computer science. This course was 4 credit and has one practical component. The practical component consists of some standard graph theory algorithms which you are supposed to implement in the programming language C. Of course, you must be familiar with the programming language C from your first semester course, Programming and Data Structures. Graph theory is one of the very interesting field of mathematics. One of the interesting thing about graph theory is that it requires least knowledge about other subjects like algebra or differential equations or analysis. Of course, what it requires is some mathematical understanding, mathematical maturity about, for example, what a proof is and how to prove different statements. And for this, of course, this may happen that for many students, mathematical maturity comes after studying a lot of courses. What I want to say is that you need basically the concepts of logic and proofs to understand this course fully. So I would now specifically introduce what is a graph and how graphs arise and how to model real world problems through graphs, and then I will give you some basic definitions and results. So first let's look at the definition of a graph. A graph is a pair of sets, namely V and E, where V is called the vertex set of G. It must be a non-empty set, and E is a set of two element subsets of V. Is called the edge set. Now, two element subsets of V means E is a collection of unordered pairs of the elements of V. So each edge has two endpoints, namely the vertices of G. Graphs are better represented through points and lines on a plane. So a graph can be represented by drawing vertices as points and each edge by a line that joins two vertices, and of course these vertices may not be distinct. That means an edge may have the same endpoints. For example, let's consider the graph as seen here. For example, we have the vertex set 1, 2, 3, 4, and the edge set consists of the elements 1, 2, 1, 3, 1, 4, 2, 4, and 3, 3. We are representing these vertices by 4 dots, as you can see, 1, 2, 3, and 4, and the edges are the lines that join corresponding endpoints. For example, the edge 1, 2 is just the edge that connects the vertices 1 and 2. Likewise, the edge 1, 3 is the edge that connects the vertices 1 and 3. You can see that the edge 3, 3 has both the endpoints equal, that is, it has just one endpoint. namely 3. So in that case, we have started the line and ended with at the same vertex. Let's look at another example. In this case, we have the vertex set consists of 6 elements, namely 1, 2, 3, 4, 5 and 6, and the edge set consists of all 2 element subsets of V. So in this case, we can draw this graph as you can see in the picture. Here every vertex is adjacent, every vertex has an edge incident to another vertex. That means for every pair you can see there is an edge joining those vertices. There is another example which has the same vertex set 1, 2, 3, 4, 5, 6, but in this case the edge set is empty. We can see that edge set, there is no edge in this graph. So it only has the endpoints, that it only has the vertices. Now we shall talk about the concepts of loops and parallel edges. An edge E equal to UV of a graph G is called a loop if U equals to V. That means an edge is called a loop if its both endpoints are the same, as we have seen in the previous example. And two edges E1 and E2 are called parallel if they have the same endpoints. That means the endpoints of one edge are precisely the same of the endpoints of the another edge. In that case, those two edges are called parallel. For example, in this graph, we can see that there is a loop incident at the vertex V, and there are two parallel edges, both have the same endpoints U and V. The concept of loops and parallel edges gives a graph which is often also called a multigraph. And when a graph does not have all such edges, that means a graph that does not have loops and parallel edges, is called a simple graph. Simple graph has very most of the times we shall in this course you will encounter simple graphs, and the concepts and results derived for simple graphs will be mostly applicable to in general graphs, that means in multigraphs as well. So now, for example, there are three graphs here. In the leftmost graph, you can see that there are loop as well as parallel edges. In the middle graph, you can see that there is no loop, but there are some parallel edges. On the rightmost graph, you can see that there is no loop and no parallel edges. So this graph is a simple graph. So after having basic understanding what a graph is and what are its elements, I would just talk about how graphs arise and what are the applications, what are specific applications of graph theory. The first application I would talk about is job assignments, and this gives the concept of matching. Suppose you are an employer and you advertise and posts and vacancies, and there are m applicants for these vacancies. Of course, since you have advertised and post, you would be interested in filling all these and posts, and each post requires certain eligibility conditions. Some applicants might have applied for more than one job, and in that case as you will be interested in finding suitable candidates in such a way that each candidate gets exactly one job. So this problem can be transformed into a graph theoretical problem and solved through graph theoretical concepts. This problem can also be stated in terms of marriage problem. Suppose there are n boys and m girls, and you are you have to find a match for each girl. So in that case, you are essentially finding a matching for each girl. You have to find some suitable boy, so that each girl gets matched to exactly one boy. So these problems can be solved through graph theoretical techniques, and it was the mathematician P. Hall who first observed that what is the necessary condition for solving such a problem. For example, if there are n jobs and m applicants, and if you are interested in filling all these jobs, then first and very necessary condition is that the number of applicants must be more than the number of jobs. Of course, this does not guarantee that all the jobs will be filled the way you want. For example, let's stick to a specific case. Suppose you have 5 jobs and 10 applicants, and all these 10 applicants are eligible only for 2 jobs. So in that case, you can't fill all the 5 jobs. Remaining 3 jobs will not find any qualified candidate. So the mathematician Hall found a sufficient condition in terms of graph theoretical representation, which you will study in this course. The next problem is networks and connectivity. Consider you have a communications network, or it could be a social network as well, and you are interested in finding the weakest points in the network. That means the points which are vulnerable to network disruptions. So in that case, those networks can be represented via graphs, and in that case we can find the connectivity of the graph, which gives us how robust or weak our graph is. And the third problem that is related to graph theory and has profound impact on graph theory is maps and coloring, the map coloring problem. You see any map of any state or any country, or even of any world map, you find that the map uses at most 4 colors. So that why is it the case? Map coloring, suppose, let me first define what we mean by a map coloring. Map coloring means, suppose you have every state represents some region, and every state has a well-defined boundary. So any 2 states that share a boundary, that must get a different color. So when you do color all the states in this way, you will end up that you do not need more than 4 colors, and this is called, in fact there is a 4 color problem, a 4 color theorem, which was solved just not only few years back. So after now looking at some applications, I would go into some definitions and concepts. The first thing that related to a graph is the order. Order of a graph is nothing but just the number of vertices in it, and we shall denote it by the notation NG, which is just the cardinality of its vertex set. Similarly, a graph also has a size, and which is the number of edges it has. and we shall use notation mg to denote the size of a graph G. Now, you know that what a simple graph is. That means a graph which has no loops or parallel edges. I ask, what is the maximum size of a simple graph? So in a simple graph, you can see that for any pair of vertices, there is at most one edge between them. So, and now since there are n choose 2 pairs, that means nc2 pairs, so the number of edges in the graph is at most nc2. That is, nc2 is the maximum size of a simple graph having n vertices. Now there is a concept of neighbors and neighborhood of a vertex. We call two vertices u and v of a graph G neighbors or adjacent if u, v is an edge of G. That means u and v are connected by an edge. In that case, u and v are called neighbors or adjacent. For example, in this graph, you can see that W is a neighbor of both u as well as v. However, u and v are not neighbors of each other. The neighborhood of a vertex of a graph G is the set of all those vertices which are adjacent to V. That is, all the neighbors of V is called the neighborhood of V. For example, in this graph you can see that vertex V is adjacent to all the vertices which are colored red, that is the vertices V1, V2, V3, V4, V5. So all these vertices form a neighborhood of V. However, you can see that each of these vertices has exactly one neighbor, namely V. Now there is another concept related to graphs, and it is the union of two graphs. So given two graphs G1 and G2, the union of G1 and G2 is the graph VG, graph G1 union G2, which has vertex set VG equal to VG1 union VG2 and edge set EG equal to EG1 union EG2. That means we just take, to find the union of two graphs G1 and G2, we just take the union of their vertices as well as the union of their edges. For example, let's look at the graphs G1 and G2 shown here. The graph G1 has 4 vertices U1, U2, U3 and U4, which each of them is adjacent to every other, and the graph G2 has also 4 vertices, namely U1, U2 and V1, V2, but there are only 2 edges in G2, U1, U2 and V1, V2. Now the union of G1 and G2 is the graph shown below, which consists of G1 along with only one edge of G2, because you can see that the edge U1, U2 appears in both G1 and G2, so that will occur only once in the union. Similarly, if you consider two graphs G1 and G2, here G1 is the same graph as we have taken previously, and G2 is a graph which consists of 5 vertices, u1, u2, u4, u3, u4 are the same as they are the vertices in G1, and u5 is a new vertex. So the G1 and G2 consists of 5 vertices, namely u1, u2, u3, u4 and u5. And now you can see that in G1 union G2, u5 is adjacent to all the 4 vertices u1 to u4, because in G2 it is adjacent to all the 4 vertices of G1. And now we come to the concept of cliques and independent sets. It happens that a graph consists of a set of vertices which are pairwise adjacent, that is, which are pairwise neighbors of each other. And it might also occur that there is a set of vertices where none is connected to each. So such concepts gives the concept, such notions give the concepts of cliques and independent sets. So first let's define what we mean by a clique. A set of pairwise adjacent vertices of a graph is called a clique, and a set of pairwise non-adjacent vertices is called an independent set. For example, let's look at this graph. The vertices shown in red are adjacent to each other, pairwise adjacent to each other, and hence they form a clique. On the other hand, if you look at the vertices, say V3 and V5, then you can see that they are not adjacent, and in fact V3, V4, V5 are two pairwise non-adjacent, and hence V3, V4, V5 form an independent set. Another concept related to a graph, related to a vertex, is the degree of a vertex. It is defined as the number of edges incident on V, where each loop is counted twice. That means to find the degree of a vertex, you need to count the edges which are incident on V, and if there is any loop incident, then that loop will be counted twice. And when G is a simple graph, in that case the degree of a vertex is nothing but the cardinality of its neighborhood. That means the number of neighbors we hedge, because in that case there is exactly one edge incident for each neighbor on V. For example, in the graph shown here, you can see that the degree of vertex U is 1, because there is exactly one edge incident on it. On the other hand, the degree of vertex V is 7, because there are 3 loops on it and there is one non-loop edge. So each of these loops is counted twice, so which the 3 loops give 6 and the non-loop edge gives 1. So the degree of the vertex V becomes 7. The vertex W is not adjacent to any vertex, so that is, there is no edge incident on it, and hence its degree is 0. Now there is very interesting result related to degrees of a graph and the number of edges it has, and it is often known as handshaking lemma. In fact, it is one of the fundamental results related to fundamental results concerning graphs. So if G is a graph with m edges, then this result says that the sum of the degrees of all the vertices of G equals twice the number of edges. That is sum of dV, where V is an edge, V is a vertex, then this quantity becomes twice the number of edges, 2m. We can see this. Let's look at some examples. Just consider the graph G here. The vertices, you look at the edge V1, V3. So when you count the degree of V1, we are counting the edge once, and when we count the degree of V3, again we are counting the edge V1, V3 once. So for each counting, the edge, every edge is counted exactly twice. This means that if we sum all the vertex degrees, and that quantity must be exactly twice the number of edges. So this is the proof is very simple. Each edge contributes exactly 2 to the degree sum dV, and hence the result. Now there is a concept of complete graph and null graph. We shall see what we mean by a complete graph. An n vertex simple graph G is said to be complete if the degree of V is n minus 1 for all vertices V of G. That means if each vertex of the graph is adjacent to all the remaining vertices, then the graph is called a complete graph. That is, there is no edge left, or it contains, in fact it contains the maximum number of edges. For example, look at this graph. You can see that every vertex is adjacent to every other. So this is a complete graph. Now on the other hand, if every vertex has degree 0, in that case G is called a null graph. That means if no vertex is adjacent to any vertex, then the graph is called a null graph. For example, look at this graph. Here every vertex has degree 0. So this is a null graph. We shall use the notation Kn to denote a complete graph on n vertices. For example, K4 and K5 are shown here. K4 has 4 vertices where each vertex is adjacent to every other. Likewise, K5 has 5 vertices and each vertex is adjacent to every other. And likewise, you can see K6. Now you might be interested in what is the size of a complete graph on n vertices. That is, what is the size of Kn? We know that Kn has n choose 2 pairs of vertices. That is, there are nc2 pairs, and for each pair there is exactly one edge that connects the 2 vertices. So there are exactly n choose 2 edges in Kn. That is, the size of Kn is n choose 2. Now the concept of degree gives another concept. It classifies the vertices into even and odd classes. An odd vertex is one which has degree odd, and even vertex is one which has degree even. For example, look at this graph. All the vertices here are odd. because you can see that all have odd degrees. Now the question arises, how many odd vertices does a graph have? And this is actually related to the handshaking lemma. In this graph we can see that there are 4 odd vertices. On the other hand, if you look at this graph, there are exactly 2 odd vertices. One has degree 1 and another has degree 3. Now look at these graphs. The graph on the left has all vertices odd, that is, it has 4 odd vertices. On the other hand, the graph on the right has no vertex of odd degree. That means it has no odd vertices. That is, it has 0 odd vertices. So in all these examples, you have seen that the number of odd vertices a graph has is an even number. And in fact, this is not a coincidence, it is a well established result which follows from the handshaking lemma. It says that every graph has an even number of odd vertices. We can prove it using handshaking lemma. Note that the degree sum dV can be splitted into 2 parts, namely over the set where V is odd and over the set where V is even. So still the sum is twice the number of edges. So now look at, on the right hand side we have an even number, and hence the left hand side must also be even. But if you look at the quantity, the second quantity dV, the sum dV where V is an even vertex, this quantity is even number because dV is even, and hence the quantity sum dV where V is odd must be an even number, right? So now what does this mean? Sum dV is even and V is where V is an odd vertex, that is, the set S which contains all the odd vertices must have an even number of elements, and therefore this proves that every graph has even number of odd vertices. Now let's look at some problems. Does there exist a graph with vertex degrees 1, 2, 3, 4, 4, 5? If you just look at the vertex degrees and just sum those degrees, or you can just look at only the vertices which have odd degree. So there are, the first vertex is odd, third vertex is also odd, and then sixth vertex is also odd. So there are only 3 vertices of odd degree, but we have just seen that the number of odd vertices must be even. So there exists no such graph. Now we ask, is there a simple graph with n greater than or equal to 2 vertices all having distinct degrees? So let's assume that such a graph exists. Then what happens? So if such a graph exists means it cannot have isolated vertices, because isolated vertices means that suppose there is some isolated vertex V, then the remaining vertices cannot be adjacent to V because V has degree 0. Okay, so the remaining degrees are from 1 to n minus 2, right? The remaining degrees will be 1, 2, 3 or up to n minus 2, but there are n minus 1 vertices, and by the pigeonhole principle you know that if there are more objects than the boxes, then some box would get more than one object. So now here we have n minus 2 degrees and n minus 1 vertices. So some vertices must get equal degree, which is not possible. So the graph cannot have isolated vertices. Now we have dv is greater than or equal to 1 for all vertices. But we also have that dv is less than or equal to n minus 1 for all vertices, because no vertex can be adjacent to more than n minus 1, because the graph is simple. So apart from the vertex itself, there are n minus 1 vertices which can be the vertex adjacent to. So the available degrees for the vertex, for the vertices are 1, 2, 3 up to n minus 1. But now there are n vertices and n minus 1 degrees. So again by pigeonhole principle, some vertices must have equal degree, which is not possible. So so there is no such graph which has, no such simple graph which has all vertices of distinct degrees. That means in every graph, in every simple graph, there are at least 2 vertices that have the same degree. Now there is another concept of graphs which also arises from the degree, and it is the concept of regular graphs. A graph is said to be regular if all its vertices have the same degree, and if all vertices, for example, have degree k, then the graph is called k regular. For example, look at these two graphs. On the graph in the left, we can see that each vertex has degree 4. So this is a 4 regular graph. And the graph on the right, you can see that each vertex has degree 2. So this graph is a 2 regular graph. Now there is a question: when does a k regular graph exist on n vertices? So k regular graph means each vertex has degree k and there are n vertices. So if you just apply the handshaking lemma, you will find that the sum of the vertex degrees, because suppose there are n vertices, so we sum the vertex degrees from 1 to n. Since each degree is k, so this sum comes out to nk, which is equal to twice the number of edges. So on the right hand side we have an even number, and hence the left hand side must also be even, that is either n or k must be an even number. So an n vertex graph can be k regular only when at least one of k and n is even. Now this also gives us, the degree concept also gives us the concept of even graphs. We have seen just now the concept of k regular graph. The concept of even graph is slightly different. A graph is called even if all its vertices have even degree, that is all its vertices are even. Note that regular graphs and even graph are not the same. For example, look at the graph on the left. look at the degrees of its vertices, you can see that each vertex has degree either 4 or 2. That means the graph is an even graph. However, not all vertices have the same degree, so it is not a regular graph but an even graph. On the other hand, the graph on the right is a regular graph as well as an even graph, because all vertices have the same degree, which is an even number. Now look at this graph. Is it regular? No, because you can see that all vertices do not have the same degree. Is it even? The answer is yes, because all vertices have degree 0, 2 or 4, and all these are even numbers. So this graph is an even graph. Another concept of graph theory is the concept of subgraph. Intuitively, a subgraph is just a portion of a graph. Of course, the portion must itself be a graph. So, graph H is said to be a subgraph of a graph G if VH is a subset of VG and EH is a subset of EG. That is, the vertex sets and edge set both are respectively the subsets of the vertex set and edge sets of the original graph. For example, in the graph shown here, look at the graph shown above. The vertices in red are the vertices 2, 5, 7, 8, and we have extracted all these vertices along with their edges, which is shown below. So this is a subgraph of the graph shown above, because the vertex set is just a subset of the graph, as well as the edge set is also a subset of the edge set of the graph. Now look at this graph. In this case, we have extracted the vertices, the portion of the above graph from 2, 1, 6 and 5 and all the edges between them. So this is also a subgraph. So subgraph, now there is a concept of induced subgraph. Induced subgraph is a subgraph of G if its edge set EH equals, it contains all those edges of G whose endpoints are also in H. That means an induced subgraph is that subgraph of G in which if any two vertices are adjacent in the original graph G, then those must also be adjacent in H. For example, again consider the graph. In the graph shown above, you can see that the red vertices are 2, 5, 7 and 8 along with their red edges. We have extracted all these vertices but except the edge 2, 7. So since 2, 7 are the vertices of this subgraph as well as the vertices of the original graph, but in the original graph 2 and 7 are adjacent, whereas in this subgraph they are not, and hence this subgraph is not an induced subgraph. Likewise, the concept of induced subgraph, there is a concept of spanning subgraph. The spanning subgraph is nothing but a subgraph that just contains as many vertices as the graph itself. That means it contains all the vertices of the original graph. Now, we ask you the question, let H be a spanning induced subgraph of a graph G. Spanning induced, that means H is a spanning subgraph as well as an induced subgraph of G. So what can we say about the graph H itself? So first of all, you find that H is a spanning subgraph of G. It means that the vertex set of H must be the same as the vertex set of G. That is VH equal to VG. And since H is an induced subgraph, it means that it contains precisely those edges whose endpoints are adjacent in G. And since it contains all the vertices of G, EH becomes equal to EG, and therefore H is nothing but the graph itself. So, dear learners, in this session we have seen the concepts, we have seen the introduction to graph theory, we have seen many concepts like the graph, what we mean by a graph, how graphs can be used to model real world problems and what are the applications, and we have seen certain basic concepts related to graph theory that you would be using throughout this course. For example, we have defined what we mean by the simple graph, what is an order and size of a graph, what are the neighborhoods and degrees, how to find the union of two graphs, what are cliques and independent sets, and we have discussed a fundamental result related to graph theory, namely the handshaking lemma, and we have also looked at what we mean by a complete graph or a null graph. We have defined the concepts of regular graphs, even graphs, and some results related to them. For example, under what conditions a regular graph has the edges, what are the subgraphs, induced subgraphs and spanning subgraphs. So with this we end the session here.